Hello all, welcome to lesson number 2 for Calculus AB. This lesson is on limits graphically. The first lesson we talked about was limits to infinity and negative infinity. And in this particular lesson, we're going to look at graphs and we're going to take limits on the left and right hand side. We're going to figure out if the overall limit exists, where something's defined, and then ultimately we're going to discuss if something is continuous at a particular value. So let's go ahead and look at a very easy, really awesome graph here at number 1. And what we talked about in the very first lesson is how to read notation for limits. And so this should be pretty familiar to you guys. The only thing that I want to really stress right here initially is the fact that for this first one, it's asking for the limit as x approaches 0, and there's a little plus sign up here on the upper right hand side of the 0. And that just means that it's to the right. Okay, so this little plus sign right here just means that this is a right hand limit. And so I'm going to abbreviate that right hand limit. And this little less than sign, this little negative sign right here is going to be a left hand limit. And so we're going to talk a little bit more about that as we do this problem. So I want you guys to realize that for this problem, we're just focusing on 0, right? So we're just focusing on 0. So for the yellow, here's how I kind of tell it to my students. So like this is our street, right? This is the street that we all want to get to. So we want to get to the street x equals 0, right? Because that's the line for x equals 0. So everything's going to 0. So what we want to do first is this is saying that we want to go to the right. So again, I'm going to write this in purple. So right hand limit. So this little guy right here symbolizes that this is the right hand side. So we're traveling along this graph. We're traveling along the graph from the right. So we're on the right side of our line right here, x equals 0. And then we hit the line. Right, we hit the line right here at y equals 2. So the limit as x approaches 0 from the right of our function, and this is our function f of x right here, our graph, is going to be equal to 2. What this is saying is that as our function approaches 0 from the right, the corresponding y value is getting close to 2. It doesn't have to guarantee 2, but we're getting really close to 2. We're approaching 2 from the right. And then if I were to ask you guys to look to the left-hand side, so this is our left-hand limit, so this is the left-hand limit, then we would go and say, okay, now let's start going on the left-hand side. So we're approaching our street from the left-hand side. And again, just like before, we hit our line, our graph, x equals 0 at 2, right? At equals 2. So again, our corresponding y value is also at 2. In order for the overall limit to be equal, right, in order for this to exist, all that you have to do, we've actually done all the work for it. In order for the overall limit to exist, the right-hand limit of our function must be equal to the left-hand limit of the function. That's it, ladies and gentlemen. So if these two numbers are the same, as they clearly are, the value for the overall limit is going to be 2. If these numbers are not the same, it's going to be does not exist. It's as simple as that. It's as simple as that. And then this last part here, I went ahead and erased everything for us. So this last part right here, f of 0, well, this is just algebra 1. So when x is equal to 0, well, what is the y value? And the y value here is equal to 2. So notice that all of these values are actually equal to 2. Well, the only thing that I really care about that's equal to 2 are these two values right here. That these two things are equal to each other. And if this is equal to this, then these two things are also equal to this. So this is where we really want to focus on, is that this limit is equal to this point of this point that we defined at x equals 0. So what does it mean to be continuous? So guys, let me just say really quickly, in layman's terms, continuity just means that I can go and trace my graph along, and I do not have to pick up my pencil, right? So I can go anywhere on this graph. So this whole graph actually is continuous everywhere. But we're only focused really on, at this particular example, x equals 0. But what does it mean in the calculus world? And these are the definitions that you guys need to know. Notation is really important here, and so we have to make sure we're good with it. So the first thing that we're going to say is that in order for something to be continuous, the point, first of all, has to be defined. Okay, so what this just means, and we all love me some visuals, is that at x equals x, or x equals c, x equals c, I have some value defined at a. So there's a point that's defined there. The next thing that's really important is that the overall limit, the limit as x approaches c of our function, has to also equal a. Okay, and then like we said before, in order for that to occur, the limit as x approaches c from the right of f of x must be equal to the limit as x approaches c from the left. So as we're going from the left and the right of our graph, we have the same value. So then I can go back up here to my graph and I say, okay, again, it doesn't really matter what's happening until I get to this. And so there's the first one. And then I can just do something like this. And so you can see that the limit here to the left and to the right are also equal to each other. And so the most important thing here is that for all of it to be continuous, so this is right now the true definition of continuity, but you need to show these particular steps, is does my point that's defined equal the limit? Because just because the limit exists does not mean that it's continuous, and we're going to do that example in a second. So it's got to, this has to be equal to each other. So f of c has to be equal to the limit as x approaches c of f of x. And it just means that if I'm going to the left, I'm going to the right, and then also at that point, that they're all defined at the same value. Okay, as it was up here in this example. So what we can say about this, is that f of x is continuous, and we can abbreviate continuous as this, at x equals 0. And actually it's continuous everywhere, but like I said, we only really care about where x is equal to 0. So that's our first example, and it's really important that you guys know this. In lesson number 4, we're going to talk about how to write out continuity a lot more, so this will be second nature to you once we get into lesson number 4. Okay, so let's look at the next example. And so in this particular problem right here, ladies and gentlemen, notice that everything is approaching -1, -1, -1, -1, and f of -1. So we're going to go and do our little graph. And I'm going to be a little, we're here, I'm just going to, so we can see it. But we're approaching this line, right? We're approaching this line. So let's look at what we have in the first part. So the first part says that we're looking at x approaching -1. And again, notice that the first part, this is the negative part, right? That's -1. But this plus right here means it's a right-hand limit. All right, so remember that anything that's a superscript is just for right-hand, left-hand limit. So I'm approaching -1 from the right, right? So we're going down our graph to the right. And again, we're looking at the corresponding y value when we get here. Well, this graph is approaching 0, right? We're getting to 0. So this is going to be 0. If I look at it from the left, which is this left hand right here, so -1 to the left, right? So -1 to the left, that's what those mean. So this is the left hand limit. And so I'm approaching from the left, I'm also hitting 0. Right? I'm hitting this y value at 0. So again, ladies and gentlemen, I don't have to do very much work now. Since these two things are equal to each other, then I can automatically say that this overall limit has to be equal to 0. Okay? They have to be equal to 0. Now, let's look at the next part. It says, what is f of -1? Well, f of -1 is actually an open circle here. So it means it's undefined. It's undefined. So what can we say about this? Well, we can't say it's continuous. We can't say this is continuous at x equals -1 because f of c, which in this case is f of -1, is not equal to the limit. 0 is not equal to undefined. So it's not continuous. So I can say that this is not continuous at x equals -1. Now, the beautiful thing about this is that we have a special name for this. And we call this removable discontinuity. And yes, you do need to know these words. Okay, so removable discontinuity is the calculus. Let's go back to Algebra 2 and pre-calculus. Let's say, okay, how would you recognize this graphically? Graphically, from what you've learned in the previous courses, well, whenever you have a graph that's got a hole in it. Okay, so anywhere you see a hole, that's where you can have removable discontinuity. Another thing that I really want to stress with you guys about this is that there are 3 types of discontinuities we're going to discuss in this class. There are 4 of them, but we're going to talk about 3 of them particularly. And so removable discontinuity is the only discontinuity where the limit, the overall limit, will always exist. It will always exist. Okay, so that means that the left-hand limit will always equal the left-hand limit will always, well, that's the right-hand limit, but the right-hand limit is always going to be equal to the left-hand limit. Okay, and therefore this overall limit is going to exist. So the other two discontinuities, the limit's not going to exist at all. So if I ever say to you guys, let's have a function that's discontinuous, however, the limit's going to be equal to a number, you already know it's removable and you know there's a hole there. Okay? So that's the thing I want to do. I also want to just add to this problem that if we're looking at this a little bit more in detail, I can also say to you guys that f of c may exist. Okay? It doesn't have to be undefined. So if I had maybe moved this point here, then you would have told me that f of -1 is now equal to -1. All right? And so, again, still not continuous because these two numbers aren't equal to each other. So this may or may not exist. This is not a guarantee, but I will tell you that for removable discontinuity, the limit will always exist. All right, so that's the first of two types of discontinuity. We're going to do two more and see what you guys can do with that. So we have continuity, and now we have removable discontinuity. So let's go into the next example. Okay, so for example number 3, we have, again, we're looking at x equals 1, right? X equals 1. I'm not going to draw the line here, but you guys can just visualize that there's a line for this. So we're looking at x equals 1 from the right, all right? So from the right. So we're going from the right, and we're approaching x equals 1. So we want, you know what, I'm just going to do it, whatever. I have to do it. So we're approaching this line, right? X equals 1. So when we approach this line right here, we see that the corresponding y value is actually equal to -2. So again, this is a right-hand limit. I want to stress really quickly to you guys, it doesn't matter if this is open or closed. Like I said, this is a limit as x approaches 1 from the right. It's not that it's going to be -2, it's just what it's approaching. So this can be open or closed. It does not matter, all right? It does not matter. So with that being said, if I'm approaching it from the left, right, if I go to the left-hand limit, so left-hand limit, 0 to the left, I go to the left, and again, it doesn't matter what's happening over here. I could be crazy like this, and then start going like, it doesn't matter. All I care about is really what's happening right here. What's happening is x approaches 1 from the left, and that is at -3, right? That's at -3. So we can automatically say a lot of things about this function, right? The first thing is we know for a fact that the limit does not exist. The limit does not exist. I always go ahead and mark out the equal sign because, you know, it can't be equals, it does not exist, but, you know, I won't mind if you do or don't. But it does not exist. So right here, I know it's discontinuous because in order for it to be continuous, all right, in order for it to be continuous, the first thing we discussed is one of the two criteria in order for this third thing to be true is that the limit has to exist and have a value of a or some number, okay? So with that being said, I know it's not continuous. So I can immediately say that f of x is not continuous at x equals 1, okay? But we want a little bit more than that. So we also want to know what f of 1 is. So f of 1, this is going to tell us, this is going to be whether it's open or closed, right? Open or closed. It was getting a little crazy over here, so I had to erase all that stuff. So this is talking about where it's defined, right? So f of 1 is defined actually where it's solid, right? It's a closed-end dot, so this is going to be equal to -2, all right? So we can now say that this is not continuous at x equals +1. And so what we call this guy is we call this jump. And so again, I told you guys for removable, we think about holes. Well, let's go back to Algebra 2 pre-calculus for a second and talk about jump. So jump is always going to represent a piecewise function. A piecewise function. Okay? And then the other thing that I always just tell students, and this just is really silly, is that, you know, we're walking along our graph, we're walking along. In order for us to get here, we have to jump. We have to jump. Or let's say it's down here, then we have to jump down. So we have to literally jump, right? We have to jump. So it's a jump discontinuity. And so let's talk about the criteria for jump discontinuity. Well, the first thing is that the limit as x approaches c of f of x will never exist. Okay, it's never going to exist. Which means that the left-hand limit is never going to equal the right-hand limit. Okay, so that's really what we want to get out of that. And that's unlike removable discontinuity, because for removable, the limit will always exist. Because remember, all we're looking for is a hole. All right, and then just like I've said before in the other example, f of c may exist. Okay, in this case, it did. This one did. I could have an open right here. It could be open and nothing would be defined there. So once we know the limit doesn't exist, right? Once we know the limit doesn't exist, then we can obviously say that it's not continuous. And we will do some algebra problems as well, all right? So this is just how to look at it graphically. So we'll get to algebra in lesson number 3. So right now, just visually looking at this, if it has a hole, it's automatically removable. That's as simple as it can be. If it's got a piecewise function, then it's a jump discontinuity. All right, so those are your two. Let's do our last one, and we're going to solidify this down here. So example number 4, again, we're looking at x equals 1 from the right to the left and overall at 1. So for this particular example, 1 to the right. So here, so it's already, the line's drawn for us right now, right? Here it is. That's all we care about. So if we're going to the right, going to the right, look at what's happening to our y values, right? Our y value. Because for everything we've done up to this point, we've always looked at the corresponding y value, right? For example, number 3, when we're going to the right, we looked at the corresponding y value, which is why we wrote a -2. From 1 to the left, we look at the y value. That's why we wrote a -3. So down here, what's going on with the y values? Well, this is approaching positive infinity, right? This is going to positive infinity. Some of you guys may realize that in your pre-calc classes, they say that, okay, you can also write does not exist. In the calculus world, both of these are completely fine, right? Positive infinity does not exist. Great, 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 great. If we look at the left-hand side, right, we look at the left-hand side, again, we're just approaching x equals 1. You can see that this is going to negative infinity, which is also does not exist. So a couple of things I want to make a point of here. The first thing is that these are clearly not the same thing. So this is does not exist. Okay, does not exist. So I ask my students this all the time. I said, what if this was positive infinity and this was positive infinity? Would this also be positive infinity? And so what I want you to know, what I want you to say is that the answer is no. It just does not exist. It does not exist because positive infinity and positive infinity are not the same thing. They're not even numbers. It's an idea. It's a concept. So, you know, I always make the joke, or about, not even really a joke, but, you know, how you have 2 billionaires, right? 2 billionaires. I can't assume that if 2 people are billionaires, that they have the exact same amount of money, right? And at a billion, it's not close to infinity, but you get the idea here. So you can't compare 2 billionaires and assume that they're the same value. So if any of these are infinity, it always does not exist. Okay? Does not exist. And again, this is undefined, right? This is undefined. So this one right here is pretty awesome because the easiest way to remember, there's 2 ways to say this, but the one that I like to tell my students is infinite. This is an infinite discontinuity because you can always see in the limits that they're going to infinity. Asymptotic is the other way that you can write this, and that's because there's an asymptote here. But I like to stick with infinity because that's what it is. And, you know, this is your visual. So we have a hole for removable. We have a piecewise function for a jump discontinuity, and we have infinite discontinuity for an asymptote. All right. So for this infinite discontinuity, again, like before, the limit as x approaches c of f of x will never exist. Okay. So again, that's why I said that's why removable is so awesome, because removable, it's the only limit that will exist, okay, and still be discontinuous, right? There's a lot of limits that's going to exist and it's going to be continuous, but this is for discontinuity. The other thing I want to say, and this is just usually what's happening, the limit as x approaches either one or the other, so to the right or to the left of f, usually they're going to be positive or negative infinity, okay? That's usually where it is because, again, we're approaching an asymptote. All right, so that's usually an idea for this. And just for the third time, f of c may be defined. All right. So ladies and gentlemen, that's our 3 types of discontinuity. What I'd like to do really quickly is do a nice little summary for you. Okay, so what did you get out of this little lesson, or at least what I hope you did? So to be continuous, 3 things have to occur. The first one is f of c has to equal a. All right, and x is the c value and y is the a value. So we have to be defined at the point CA. The second thing is that the limit as x approaches c, this value here of f of x, has to equal a value, in this case a. Okay, and again, in order for this to occur, the limit as x approaches c from the right of f of x must be equal to the limit as x approaches c from the left of f of x. And then thirdly, these two, number 1 and number 2, have to equal each other. Okay, now notice all the notation I'm doing here. You have to be good with this. Guys, you can't leave out the limits. You can't, I mean, students forget that all the time. You cannot leave out the limits. Okay, so that's the first part. For discontinuity, removable. Let's actually call this 4. Removable. It's going to be a whole visually, and it's the only discontinuity where the limit's going to exist. Okay, so that's pretty awesome for that one. For 5, jump, it's going to be a piecewise function. And the limit as x approaches c of f of x does not exist. Okay, and this one again, the left-hand limit does not equal the right-hand limit. And then finally, number 6 is going to be infinite, and that's going to have an asymptote, and the limit will also not exist. I'm running out of room here, I apologize. And again, this is where one of the two, if not both, limits are going to approach infinity. All right, so there we go. That is a great video. Well, not great video, but it's a good video. At least I hope it's good, on discontinuity with a little bit of continuity thrown in there. And so we're going to come back in the second video, and I'll show you guys some more examples, and we can talk about it a little bit more for you to practice.